Modular arithmetic. So what we can do is let's just do a bunch of problems, and as we go through it, I can maybe kind of go over a few things. So first problem, we have 13 to the 73 mod 4. And the first thing what I'll do is I'm going to reduce, I'm just going to look at 13 mod 4, but oh, I didn't even write the 4. 13 mod 4, but that's congruent to 1 because when you divide 4 into 13, the remainder is 1. So this is going to be an easy problem because it doesn't matter how big the exponent is. If you have 1 raised to anything, it's just going to be 1. So we got that one. So let's do another one. We have 6 to the 106. Again, let's reduce mod. Let's reduce this mod 6. We'll reduce the base mod 6. So we have 106 mod 6. And that's going to be equivalent to 4. Okay, because the remainder is 4 if you divide. I was just thinking that 6 divides into 96, so then it divides into 102, and therefore we get a remainder of 4. So then when we keep going with this, we're going to have 4 to the 126 mod 6. And so you can't, because 6 is not a prime, you can't use Fermat's little theorem here. And you can't use Euler's theorem. The 6 and 4 are not relatively prime either. So what we could do, it's a little overkill, but what we can do is you can kind of do like Chinese remainder theorem, but kind of real quickly. Like we could separate this and say 4 to the 126 mod 2 is congruent to 0. This 2 divides 4. So 4 is 0 mod 2. So it doesn't matter what the exponent is. But then we can also look at 426 mod 3. And that's just going to be congruent to 1. Um, yeah, so 4 mod 3 is 1, and so 1 raised to anything is 1. So we're looking for a number that's going to be 1 mod 3. I'm actually I'm making this into a really long problem when there's only a few options. Um, Mod 6, the only options we have are 1 to, well, 0 to 5. And if we look at, let's look at the numbers that are 0, that are 0 mod 2 from 0 to 5. So we would have 0, 2, and 4. What I should really do is write it here. 0, 2, and 4 are the numbers that satisfy 0 mod 2. And the numbers that satisfy 1 mod 3 are just 1 and 4. We can look at what's in both lists, and it's 4. So 4 is going to be our answer. Sorry, that was probably way too long for that question, but I wanted to try to hit on a few things there. So let's try another one. 111 to the 53 mod 10. That's going to be, so 111 mod 10 is just equivalent to 1, and 1 to 53 is also 1. So we got another easy one there. Keep going. Next problem. Oh, I didn't really want the sparkly. Eh, it's not terrible. All right, we'll go with the sparkly for a minute. So we got 137 to the 55 mod 4. So first what we can look at is just what is 130. Yeah, I don't like that. I don't like that at all. Let's change that. Okay. So get rid of that. Yeah, I'm erasing that too. Okay. 137 mod 4. And that's going to be Oh, we're getting a lot of things that are 1, which is not making this very interesting. 137 mod 4 is 1, and 1 to 55 is 1. All right, sorry, we'll keep going. Try to do better next time. Okay, 121 mod 7. What is that? I actually don't know what that is. 121 mod 7. So let's see, 7 goes into 98. I think 119. Yeah. Okay, so this is going to be coming to 2. So now we have, okay, so that's congruent to 2. So what we're going to have is 2 to the 141 mod 7. And now we can use Fermat's theorem, okay, because 7 is prime. And then, of course, when 7's prime, 2 has to be relatively prime because it's prime. So, but what this means is we can take this 141 and we can look at 141 mod 6, which is actually the b of 7. Totient of 7 is 6. So you can look at it either like from Euler's theorem perspective, you use this, or Fermat's theorem just says p minus 1 with p being 7, p minus 1 being 6. So let's look at 141 mod 6. Okay, 141 mod 6 is going to be congruent to 3. And then, so then what we can do is we can reduce this 2 to the 141 mod 7 is going to be congruent to 2 to the 3. You see how that simplifies significantly. 2 to the 3 is 8. 8 mod 7 is congruent to 1. Let's check that. 1's our answer. Good, good, good. Let's do another one. Yeah, so 121 mod 3 is just 1, and 1 to the 54 is 1. So that one's a little too easy. Okay, let's look at this one. So let's do it in red. So let's just look at 10 mod 2. But 10 mod 2 is just 0. This 2 divides into 10. And so 0 to anything is just going to be 0. Okay, good. So we'll try to up the difficulty level a little bit, see if we can do better that way. Okay, so we have 90 mod 22 we can look at first. So 90 mod 22, we divide 22 into 90, 22 times 4 is 88, so we're going to have a remainder of 2, so it's going to be congruent to 2. So then we're just looking at 2 to the 54 mod 22. Let's see. So we can look at this as we can kind of break it apart because 22 is not prime and 2 and 22 are not relatively prime. So we can kind of split this up. So let's look at 2 to the 54 mod 11 and 2 to the 54 mod 2. Because 2 times 11 equals 22. And we'll take this one first because that's easy. 2 mod 2 is 0, so this whole thing is going to be 0. For this one, 2 to the 54 mod 11, we can again use Fermat's theorem. 11's prime. So then we can use p minus 1, or we can p minus 1. 11 minus 1 is 10, or the totient of 11 is 10. And then just reducing 54 mod 10, we can reduce this to 2 to the 4 mod 11. 2 to the 4, 16 mod 11, that's just going to be 5. Okay, so then again, technically you could use the Chinese remainder theorem, but that's a little too much work for this case. We just want numbers that are 5 mod 11 and 2 mod 0. So let's see, if we look at 5 mod 11, that's just only be a couple items going to 22. So like we're looking at 5. It's really just 5 and 16 are the only possibilities that are 5 mod 11, right? Because you add 5 to a multiple of 11, and you add 5 to 0, you get 5. You add 5 to 11, you get 16, and you can't go past 22. So it's one of these two, but it needs to be also satisfy the second criteria, 0 mod 2, which basically says it's even, which has to be this one. Okay, good. Maybe just a couple more. I think we'll stay away from, we'll just go for stay with the random. Okay, so we're looking at 6 to the 25th mod 14. Again, not relatively prime. And notice there's no, we could look at this, but we can't reduce that any. It's already reduced. So let's bring in the exponent. I think again, let's split this up so we can look at 6 to 25 mod 2. And we can look at 6 to the 25 mod 7, because 7 times 2 equals 14. Okay, then 6 mod 2 is just going to be 0, because 6 is a multiple of 2. So there's nothing to look at there. This one's kind of interesting. So if we just look at 6 mod 7, 6 mod 7 is -1. So a really good simplification technique is using the -1, but it's just so easy to calculate. And so we can look at -1 mod 7, but we know a negative number to an odd power is just going to be negative, or not a negative number, a -1 to an odd power is -1 to an even power, it's 1. So this is actually just going to be equivalent to -1 mod 7, and that's congruent to 6 mod 7. And then we can kind of do the same thing we did in the previous problem. If we look at numbers 6 mod 7, we get 6 and 13 is 6 mod 7. And we also want it to be 0 mod 2. So we need an even number, and that's going to be 6. Okay. I think last one. I was going to say I was questioning how can my score be 2 when we've done like 10 problems, but we changed the difficulty level so it starts over. Um, yeah, so that's too bad. Okay. Last one, I think. So 13 to the 127 mod 7. And notice that 13 mod 7 is congruent to 6 mod 7. But that brings us back to where we just were, where we have, it's actually equivalent to -1 mod 7. -1 to the 127, but that's an odd power again. So then we end up with -1 mod 7, but that's just congruent to 6. That should be our final answer. Got it. And hey, thinking about the score, we can actually look. This is kind of useful as we can look at the results. 6 minutes. I feel like that was kind of slow, but I think you guys slowed me down because I'm doing a video. But anyway, we did just at the hard level. This is not counting the moderate level ones we did. So at the hard level, 27 points. That's not that great, but it's all right. And it just shows my. It's kind of interesting when you make a mistake because then you can go back and see where you went wrong. So I thought that might be interesting. I don't have the I don't think we can look at the stats. I don't have the stats working, so I can't save stats or view the history. That's unfortunate. I need to get that part working. The database is, long story short, broken. So you can't see that, but we'll get that at some point. And then, oh yeah, and then in the help, I do have some of the common techniques that we used in this using. There's probably a better I probably have another link somewhere else with the more information on Fermat's theorem, but this has some of the basics, and there's some links. I also have a modulo calculator, which I find pretty useful for exponents and like some big numbers, so the ones that are harder to calculate. So you can check that out. I'll give a link in the video, and I'll stop it there. Thank you.